Revolutionary quantum computing, Oxford Ionics and Iceberg Quantum's fault-tolerant architecture. Quantum computing's biggest roadblock isn't just creating qubits, it's making them reliable enough for real-world use. And this collaboration might hold a revolutionary key everyone's been searching for. Oxford Ionics, a trapped-ion quantum computing specialist, has teamed up with quantum architecture firm Iceberg Quantum to design fault-tolerant quantum systems. This partnership forms part of Oxford Ionics' involvement in Stage A of DARPA's Quantum Benchmarking Initiative, QBI, targeting one of the field's toughest challenges, slashing the massive hardware overhead in quantum error correction. Traditional error correction methods like surface codes demand astonishing ratios of physical qubits to logical ones, often requiring thousands of physical qubits just to support a single stable logical qubit. But here's where it gets transformative. Iceberg Quantum's focus on quantum low-density Parity-Check, qLDPC, codes flips the script. These codes use sparse, non-local structures to detect and correct errors efficiently, drastically cutting qubit overhead while enabling rapid parallel decoding. Imagine it as a streamlined security system that spots intruders without needing a guard at every door. Now, why trapped ions? Oxford Ionics hardware brings critical advantages. Long-range connectivity lets qubits talk across larger distances, combined with extended coherence times and precise gate fidelities. These features perfectly suit qLDPC's non-local operations. Iceberg Quantum has already made strides here, developing methods for universal logic gates within qLDPC frameworks. Think of it as building a complete toolkit for quantum calculations within this efficient architecture. The partnership aims to merge these innovations, accelerating practical, fault-tolerant quantum computers that need far fewer physical resources. Oxford Ionics already reports impressively low error rates in single-qubit gates, 2-qubit gates, and state preparation/measurement, SPAM, metrics essential for real-world applications. But here's the controversial angle. While trapped ions offer accuracy, skeptics argue their laser-based control systems could complicate scaling compared to superconducting rivals. Is this approach the golden ticket, or will engineering hurdles delay its promise? Weigh in below. Do you see trapped ion and qLDPC as the future, or just one piece of a larger puzzle? Ultimately, this collaboration isn't just theoretical. It's pushing research into tangible products, promising quantum solutions with reduced hardware demands. For deeper insights, explore the full announcement link in our bio. What's your take on this strategy? Could it finally bridge the gap to useful quantum computing, or are we still years from a breakthrough? Share your perspective in the comments. Accelerating quantum computing, Oxford Ionics and Iceberg Quantum's breakthrough partnership. Quantum computing stands at a thrilling crossroads, promising revolutionary advances but facing one major hurdle: error correction. This is where the collaboration between Oxford Ionics and Iceberg Quantum becomes truly exciting, as both companies are joining forces to fast-track the development of fault-tolerant quantum computing systems. But here's where it gets controversial. Fault tolerance in quantum machines is incredibly complex, and some experts question whether current approaches like qLDPC codes can deliver on their promises at scale. Oxford Ionics is taking a leading role in crafting a quantum computing architecture that emphasizes fault tolerance, an essential feature if quantum devices are to move from experimental novelties to practical tools capable of solving real-world problems without succumbing to errors. Their strategy involves integrating Iceberg Quantum's specialized knowledge of quantum low-density Parity-Check, qLDPC, codes, advanced mathematical frameworks designed to detect and correct errors in quantum bits, qubits, efficiently. For the uninitiated, think of qLDPC codes as highly sophisticated error-correcting blueprints that help maintain the fragile quantum states necessary for computations to be accurate. This partnership signifies a bold attempt to overcome one of the most substantial barriers in quantum technology by combining Oxford Ionics hardware design prowess with Iceberg Quantum's cutting-edge theoretical expertise. The implications are profound. Achieving fault-tolerant quantum computers would enable breakthroughs in fields ranging from cryptography and materials science to drug discovery, areas where classical computers struggle. And this is the part most people miss. While many players in quantum computing focus solely on qubit quantity, Oxford Ionics and Iceberg Quantum emphasize the quality and stability of these quantum systems. By addressing the error correction issue head-on, they're setting a foundation that could well define the next decade of quantum tech progress. If this sounds like a pivotal moment to you, you're not alone. Over 12,000 scientists, engineers, and IT professionals already follow innovations like this through platforms dedicated to high-performance computing, artificial intelligence, and lab informatics. They gain exclusive insights into breakthrough quantum research and practical applications shaping the future. For those eager to dive deeper and stay ahead in this rapidly evolving field, registration on such platforms offers access to tailored content across life sciences, engineering, and academia, including white papers, software updates, and real-world success stories highlighting how computing breakthroughs impact diverse industries. What do you think about the role of qLDPC codes in achieving fault tolerance? Could this alliance between Oxford Ionics and Iceberg Quantum be the game-changer they claim? Or do you see alternative error correction methods as more promising? Share your thoughts and join the conversation. Your perspective might just spark the next big idea in quantum computing. Riverlane and OQC take a leap towards fault-tolerant quantum computing with QEC integration. Quantum computing's error-fixing revolution is here. Riverlane and Oxford Quantum Circuits have just teamed up in a real-world commercial data center to deploy DeltaFlow 2, the first dedicated quantum error correction (QEC) system running live in the UK. This milestone sparks excitement and debate over how fast we can push quantum machines toward fault-tolerant operation. But here's where it gets controversial. Can this infrastructure truly scale to the million operation milestone that the UK government demands? Riverlane's announcement on July 22, 2025, revealed that DeltaFlow 2 has been installed at Centre Square's Cambridge facility, co-located with OQC's superconducting quantum computer. In plain terms, quantum error correction is like a safety net for fragile quantum bits, or qubits, which are prone to losing their delicate information. DeltaFlow 2 goes beyond previous designs by offering streaming quantum memory, a capability that continuously watches and corrects errors during computation. This continuous protection means qubits can remain useful for thousands, or even millions, of operations, a vital requirement for any scalable quantum application. Under the hood, DeltaFlow 2 combines a custom error correction chip implemented on FPGA hardware with Riverlane's proprietary software stack. The result is a universal solution that works across all leading qubit platforms, superconducting circuits, trapped ions, spin qubits, and neutral atoms. In other words, whether your quantum system uses ultracold circuits or laser-trapped ions, DeltaFlow 2 can slot right in. This universal compatibility sets it apart as the only commercially deployed QEC technology designed to serve every qubit architecture. At Centre Square, DeltaFlow 2 isn't operating in isolation. It's woven into high-performance classical computing clusters that run a digital twin, simulating and monitoring noise in the quantum processor in real time. QLOC's control hardware handles the precise gate operations and readout signals, all communicating over ultra-low latency links. This tight integration ensures that error correction routines trigger within microseconds, fast enough to catch mistakes before they cascade and destroy quantum information. The immediate goal of this deployment is to validate QEC routines, stress test system behavior under real-world conditions, and benchmark its performance. Looking ahead, Riverlane and OQC plan to demonstrate live, real-time error correction on OQC's superconducting qubits. Achieving that will prove the concept isn't just lab hype but a practical route to logical qubits that remain coherent long enough to solve meaningful problems. This work is part of the UK government-funded DECIDE project, which aims to build national expertise in quantum error correction and bolster the country's wider quantum infrastructure goals. In Gerald Mullally's words, CEO of OQC, integrating Deltaflow 2 into a commercial data center accelerates the path to commercially viable quantum computers by tackling errors at the hardware level. These efforts also support Mission 1 of the UK's National Quantum Strategy, the ambitious target of a megaQOP, defined as 1 million error-corrected quantum operations, by 2028. Deploying and testing QEC in commercial environments bridges the gap between academic demonstrations and the scalable machines that industry really needs. Quantum error correction is rapidly shifting from research labs to live installations. Although only a handful of global systems currently offer partial QEC, Riverlane's solution is already being adopted by partners like Inflection and Rigetti Computing under the guidance of the UK's National Quantum Computing Centre. This growing ecosystem reflects a rising demand for dedicated error correction hardware across the quantum hardware landscape. Riverlane's mission is clear: make quantum computing useful, sooner. Achieving that means slashing system error rates by a factor of 10,000, a feat nobody else has managed at scale. At the heart of Deltaflow is the world's most powerful quantum error decoder, powered by Riverlane's own class of patented QEC semiconductors. Today, Riverlane already supports over half of the world's quantum computing companies with its error correction stack, driving progress toward an era of computing as transformative as the industrial and digital revolutions. And this is the part most people miss: hardware-based quantum error correction could drive up system complexity and costs, prompting some to argue that software-only solutions or alternative error mitigation techniques might be more practical. Do you believe that a dedicated QEC chip is the long-term answer, or is the industry betting on the wrong horse? Will projects like DeCide truly secure the UK's lead in fault-tolerant quantum computing, or are we rushing headlong into a hardware arms race? Share your thoughts and join the debate in the comments below.